So hello everyone, good morning, afternoon, evening, whichever time zone you're coming and calling us from today. My name is Rebecca Cronin and I'm one of the customer success managers here with the Altair Data Analytics team. The customer success team are here as another point of contact for you to reach out to at any time with any questions, concerns you may have regarding Altair solutions, and if you're unable to get a hold of your account manager. We're excited you're joining us again for our Ask the Expert AI Studio webinar series. Our goal for these sessions is to provide an open time slot where you may freely drop in, and we'll do our very best to provide any assistance in answering any and all questions after demonstrating our starting topic segment. So we'll begin the session in just a few minutes, but before we dive in, let me provide a few housekeeping items. On the side, you should have a control panel where you can locate the handout section, which will have a copy of today's PowerPoint presentation that you may download. Within that PowerPoint contains some helpful web links for our AI Studio resources. You'll also notice there's a question panel. During the question panel, this is the opportunity for you to submit any questions you have regarding AI Studio, AI Hub. It does not have to be about our featured topic today. Note that we will answer our question as best as we can within the timely that we're given. And if we don't get a chance to get to your question, we will follow up within 2 to 5 business days via support ticket. So if you have anyone that's online that you think this topic that we're going to cover is interesting, please forward that invitation registration link, which you may see in the chat section. Now, I'd like to introduce you to our expert for today's session. It's Claudio. He is one of our data analytics solutions managers from our EMEA Aerospace and Defense team. His educational background and strengths are in both mechanical and process engineering. However, he has worked in the field of data science for over the last 6 years. So with no further ado, I'm going to be turning over presentation to Claudio so we could dive right in to our topic of featured selection options. So Claudio, handing the reins over.
Yes.
And I see your AI Studio interface.
I just need to quickly switch my screen. Now you should see my feature selection
little PowerPoint
slide.
Yes.
A PowerPoint slide
yes,
with feature selection on it. Perfect.
Perfect. Yep.
Because first of all, hello everyone. Today, what I get told to talk a little bit about is about feature selection. And when we talk about feature selection, we will talk about different things. And first of all, it's quite important to do feature selection because always when we start machine learning, first, we need to have some data. Then we need to have some data in a good quality. But then suddenly we have enough data, but then we have the important question, which of this data we should use, or which of this data we could use. For sure, we can put everything into a machine learning model, but is it advised to do so? Maybe, maybe not. And as well, it will be computational heavy. And maybe we'll use a bunch of data which is just useless to what we want to achieve. And to work better with our features, feature selection is one of the core concepts. And what I want to cover today is basically, I want to talk a little bit about how you can use feature selection in AI Studio. And when we talk about feature collection, we talk about filter methods, like we talk about filter methods. This is basically always univariate. Univariate means we have one variable and check it towards the influence to our target variable. And there we have commonly used like correlation, which is typically used for to understand the relation between one numerical variable to another numerical variable. Or we can use the chi-squared. It's not for numerical versus numerical. A chi-squared, for instance, is used when you want to use it if you want to evaluate a nominal variable versus another nominal variable. And as well, we're having information gain and Gini index, which actually you use them kind of as a filter method, but actually those are model weights or like embedded method for a model, but later more to that. Another typically used is an ANOVA you could use, which is a method to understand the variance or just check in general if there's a variance threshold. Another thing you can use as well is the mutual information to understand how different features can be used against each other. But how you can use them now in AI Studio, I'm going to quickly show to you. So here we are in AI Studio. Rebecca, can you just quickly confirm that you can see AI Studio?
Yes, I see AI Studio. Perfect.
So here, if we want to do now like understand the filter methods, we can either navigate manually through modeling to feature weights and to see here like our matrices, so correlation, ANOVA, and as well seeing here our features. But as well, we could quickly look here, for instance, I'm interested in my chi-squared. Then I would get to my chi-squared quite quickly. Same goes with correlation, ANOVA, so on, so on, so on. So maybe as a first step, let's let AI Studio crash. Maybe as a first step, like we will now look into how we will use all of those methods. And while I'm quickly restarting AI Studio, here we are. Let's maybe check with the first one, so a correlation matrix. So you all know the trick. I now want to use the correlation matrix, but actually I don't even know how to use it. So maybe I should check in the help section for a quick example. And we're having here an example set where we want to know like play, no play, and for instance, for the temperature or the humidity or the outlook, we want to check how are those factors correlating. So without doing too much, we will have the option to see now how the things are correlating. So wind versus wind always has a linear dependency on one. The important thing, correlation always checks linear dependencies. So for instance, how does play and wind has in terms of linear dependency? What has temperature in terms of humidity in terms of linear dependency? And we can see all of those having quite a low linear correlation. Another thing, when we're talking about matrix views, we will just quickly cover the ANOVA next. So instead of using this one, we will go to the ANOVA. We just quickly delete here everything out. I will just take quickly again the tutorial process. I don't want to save it. So again, we have an example set of our golf players, and the ANOVA will now check what is the mean of the temperature and the humidity towards the play. So it will calculate if the mean value of the temperature of the no is different than the mean value of the yes. So basically, we will check the distributions of the temperature and humidity if they are splittable towards play or towards so we take the play, it will do for all nominal values. Every time a numerical value has a relationship to a nominal one, ANOVA will be able to calculate it. And what does it mean? Like, so it will calculate how the temperature as a feature, what the mean has towards the group play in terms of variance, and we'll check the humidity, what humidity has in terms of variance towards the play. And by that you can rank and you can see what is more important as a feature or less important as a feature. Like for instance, when here we would get 0, we would know, okay, there's no variance which can explain the play and we want to predict if we can play or not play. It's not useful. And as higher this value are, as more likely it is, it has some information we can use to predict, or like in the end have the power to predict something. So to summarize, again, a higher value, similar to the correlation, our variance will tell you this is useful or not useful. Another thing while we're at the golf data set we can do is now, we covered now, I would say, the most standard matrices one. the correlation, and the ANOVA. So let's maybe now go to, we're having a categorical target, and maybe I want to know now how the outlook and the wind, how is the influence towards the target. So basically we want to do a correlation, but correlation typically use if you have one numerical value towards a numerical target. But now what we want to do is we want to compare a nominal value like wind or outlook to a nominal target. And therefore we would now use the chi-squared index, who would exactly will do that. And now the chi-square will calculate towards us for all of those values what or how important a certain value is in terms of weight towards our target variable. So in this case, the temperature has the highest importance towards to play or not to play. So a warm temperature is more likely that we can play golf. Low temperature would mean it's less likely. And this can be again used to select your features. When you have tons of features and you have a nominal basically label, typically use a chi-squared to quickly see, okay, which of my variables I can use, I can't use. To support this, we can use some more weighted features, like for instance, information gain, which is basically describing how much of the entropy, so how much of something of the information you gain based on each split of, and we can use the Gini index, which will describe basically how pure you can create something, how much purity you can get by a feature. And as purer, as more you can basically create one class or specify one class, as more powerful such a feature is. So now we have, for instance, 3 of those. Now we could run all 3 of those. And we would now get a result for our Gini index to see, okay, what would be like having, in this case, the lowest Gini index is the best one. So in this case, the wind and the temperature would be quite good. We would again check the information gain, what would be the highest. So the outlook and the temperature would have the highest importance. And here we would have temperature and outlook. And now you recognize something. They are similar, the results, but at the same time, they are slightly different. So now we have used multiple of those feature indicators to tell us how our feature is, to describe how it basically, if our feature is important or not. But sometimes we need to do a trick. So instead of using just one, what you typically use, you use multiple ones. And then what you do is you rank them. So now in this case, for example, we first try to make it based on the correlation, then we check it based on the Gini index, based on information gain, based on the gain ratio. And then what we do is like basically you take a lot of those weights and then you combine them. Basically you add all of them one after another. Then you get like based on which one a lot of weights. And then you aggregate them and then sort them after what is the most important and reorder them. So you kind of create a score. So rarely you use just one of those. Most of the time, use a mixture of multiple of those. So what does it mean? So instead of just using one of those univariate filter methods, most of the time it makes sense to use multiple of those and then create a score of those mixture of them. And as more of those use, and then you either can rank them equally, you can put weights on some of those, depending on a use case, you can find the right way to select the right features. Because by that, you can see what is important or not important. So basically use maybe like based on the chi-squared and basically based on information gain, Gini index, maybe as well ANOVA. So you use different methods and then you will equally rank them and see like, okay, when from 3 out of 4, for instance, temperature has the highest importance, you can be quite certain that the temperature has the highest importance. The things I haven't covered yet is variance and mutual information. Variance is in the end a simple threshold where you would calculate the variance. So we're having here, by the way, that's one of my favorite operators, which I use in basically every workflow. It's called remove useless attributes. This remove useless attributes, you can specify how useful, or you define as useful, and when you don't want to have it as useful anymore. What does it mean? So it will filter out your constant values. So for instance, we're having here again a data set, and we want to get rid of all examples where there is no information gain or less information gain. So then we can specify here, I only want to use everything which has more than 60% variance, and based on this, I use those, and which is less than 60% has variance in terms of in the data we won't use. So for instance, remove useless attributes is as well perfect if you, for instance, have a constant value column now. For instance, let's quickly generate one where we name constant, we give it a 1. So we would now have in here, for instance, our constant column 1. We would run this one again. In this case, we would now can as well use 1. Oh, wait, we already have 1. Instead of 0.6, we use 1. So we don't want to have any constant value. So always zero variance excluded. So our constant value is removed. That's how you can filter or select features based on your variance. And last but not least would be the mutual information. You can just quickly use it here again. Again, it will create a matrix view and telling us how much of similar content different columns are having, different numerical columns are having. So for instance, the wind has basically no mutual information towards the temperature, while the humidity and the temperature are having some kind of mutual information. So for instance, by that you as well can see basically if you have a target, for instance, I want to predict the temperature, and humidity has quite a lot of mutual information, you should definitely include mutual information, while you can consider removing the wind because it actually doesn't have that much information. This is how you can use as well a mutual information matrix to understand what feature to select, what feature not to select. So much onto the univariate feature selection methods. So basically univariate are all the filter methods. So now let's look more across the wrapper methods. There we'll just cover the most typically one used. So let's quickly go into some, I don't want to save it, to go one example. So let's quickly run this process. We're having here a milling machine. I'm a background of engineer, so coming from production, so I love machinery data. So we're having here some data. If my machine is going to fail, not going to fail, air temperature, process temperature, the rotational speed, the torque, and the tool, how long it was used. And as well, we can check this quickly out if you like in some line charts. It's classic time series data about a milling machine. And we want to predict if a machine is going to fail or not going to fail. And I'm now having, I want to predict this maybe using a logistic regression, but I'm not quite sure what of my features I should use, I should not use. I'm using a decision tree or whatever simple model I'm using in here. So in a logistic regression, having my performance I want to apply, having this in a cross validation. And now I'm using, you will find that if you type in here feature selection, I will use the forward selection. What does forward selection means? The model will start training, first of all, with one attribute, and then one after another, it will add in every time. After one evaluation is done, it will add another variation to it. So it will be trained, first of all, maybe just for process temperature. Then it will be trained just on air temperature. Then it will be trained on process and air temperature. Then it will be trained on process, air temperature, and torque. And by that, it basically every time it adds another variable to it, another feature to it. And then in the end, it will check what was the optimal mixture of features to use for. And basically you get here then a weighting. You see, like, so it was used, the rotational speed and the torque was enough to predict a model with a 69% accuracy. So we were okay on precision recall for our 2-2 class, not the greatest, but anyhow, we can predict this with just the 2 of those, and the other 3 values we don't actually need. We as well now could quickly compare this. If there will be now a big difference between using this one and using all. Let's just quickly disable it and put it on here so we are fully comparable. And we'd see, like, in terms of accuracy, nothing changed. So in the end, what can we learn of that? We don't need all the features to predict it. And this was based on a forward selection. We could understand this. Another option to do this is as well the backwards elimination. While the forward selection already implicates in the name, we always use one step after another to add into the backward elimination. First starts with all data, and then it removes step by step the data to get to less and less, basically. So we get to the same result. We as well get to the same rotation and torque, but it's going the other way around. So it starts with all of those, and then remove step by step the and when to use what. So the backwards elimination you should always use when you have small data sets, because on big data sets you will have first a lot to use, and then you would need to remove. Well, on the forward one, if you have a big data set, you can start by step by step. And that's basically the big difference. And it really depends on the data set. If you want to have something quick, or if you have a big data set, it makes sense maybe to start with just some of those. But at the same time, sometimes it makes sense to start with Sometimes it makes sense to start with all of those, while on the other hand, it is just simpler. Like, for example, forward on my brain. So slowly. The forward selection is simpler and less computational heavy. And this is because of this, it's just more efficient. But it will never check all combinations, because if one good combination is found, it's basically, it stops. Because it will basically, if it sees the features doesn't get better, it will just stop, and it won't add new ones in. And by that as well, you run into the option of overfitting, but you can super use it well for small ones. While for the backward elimination, you will start with all the features, and then it will start removing features. Basically, it will decrease the model performance, and will see if this will have an impact by removing one feature at a time. With that, you're more likely to find the optimal set, because it will start with all features, while the forward selection will stop at one point when it doesn't find anymore a high enough gain. And with that, you're definitely sure you will find the critical features. But this is way more computational heavy than the forward selection. The other one I haven't covered now is the MR evolutionary. The evolutionary is in here. It would be just a different way how you would do it, and it would run optimized and selected based on an evolutionary method, which can be only used for regression. And the last one, which is specially used if you have a lot of data you want to select off, like for instance, we're having now a time series example of my milling machine, and it would have tons of data. Then we could use the MR. So MR stands for minimum redundancy, maximum relevance. And it's a feature selection method that aims to select the subset of features which has the maximum relevance. Maximum relevance means which has the highest importance. You can imagine, like, it checks for the features with the highest correlation towards a target variable, but at the same time it checks for the values which are having the minimum redundancy. So it will select the features which have are having the highest relevance, but which are not being collinear or not similar to each other. So it will only select those features which are relevant for the target, but not relevant between each other. So you won't have any collinear features. And especially, I won't run this now to the end, but that's an example from a client project where we used this, for instance, where you had time series data, those not just fake data, and we had to create a lot of features basically per timestamp. We created a typically time series example. We created mean, max, min, standard deviation for each of those attributes per window. So you get a lot of data and you have like 900 columns. Then MR is super nice to really spin down what are the important signals which are having the maximum relevant information, while at the same time you won't get all the collinear features. But this will calculate for at least 5 to 10 minutes on my machine, so which takes some time, so I won't go into more detail on that. But that's another nice way on how you automatically can use an algorithm for your feature selection. And coming to the third column, some machine learning models already natively have embedded methods which are basically using by nature feature selection. So what does embedded mean? So natively, already in the process of training the model, it will understand and check if the feature is useful or not useful. So tree-based method will work based on information gain of Gini index. So a tree will always take one feature, one attribute, and will check, okay, based on Gini index, how pure we can get. So how much of the one side impurity means how much, for instance, if we want to predict yes or no, how much of yes we will have on one side, how much of no we would have on the other side. Or information gain, how much of the entropy based on one split we can create to explain our problem. And based on this, we already know what is the feature which has the most information. And basically in each model training step of a tree, so decision tree, random forest, whatever, or as well GBT, XG boosted trees, in the end it's the same. We'll check in each step of the model training, they evaluate the feature importance and are checking, okay, does this make sense? Does this make no sense? While for linear regression, logistic regression, SWM and neural net, all of those will as well do this if they're using the lasso regression. So the lasso regression, in the way of finding the optimal or fitting the optimal line, it will basically drop out certain features or make it basically to zero. And with that, it shrinks basically coefficients of certain values to zero. So with that, basically it removes features, so it drops out features. And based on this function, some of the regression functions as well have the option, basically an embedded feature selection way. And how this look like, we can quickly look again at our milling machine. And then I will show you a second way how to even use this in AI Studio quite nicely. So if you would go back in here, I have something prepared in the sub-process. So in this sub-process, quickly for you to know, we're splitting the data. We're having a decision tree, and we apply it, and we see here, oh, we're having weights as an output of our decision tree. And we can check our weights, and we can see, okay, what is our most important feature? So based on the criteria we used information gain. We will see, based on information gain, the air temperature was the most important feature, then the torque, then the process temperature, then the tool wear, then the rotational speed. We could now do the same feature selection instead of the information gain as well, based on the Gini index, for instance. And based on this, the torque would be more important, the air temperature, then the process temperature and the tool. And the question is now what we should use of those. We anyway do here we might overfit, but we would check. So here we would have an accuracy of 98%. Now we would go to information gain. We would be at, check as well at 98, I guess. So 97.8. So we would be a little bit worse than the other one. So in the end, the information gain would maybe give the better model result. But as well, here we learned again, the model already does the ranking for us, what features are important to use and not important to use. And if this would be now too computational heavy, for instance, if we would now use a single decision tree, if we would now use a boosted tree, it makes sense to strip down the data set to just the important features. And we could now, for instance, check the decision tree in here if we would check the model. But that's hard to interpret and as well hard to understand. Therefore, we have a nice tool to better understand it. So we can build such a decision tree by our own and fit a data set to it. So again, we want to now train our model. We decide based on green directly what to use, what makes sense to use, what doesn't make sense to use. We can here again select how we want to have the splits measured. We want to have it based on the entropy variance. So basically it's built on the information gain. And we would run it again. And now we're having here our machine failure. And now we could run this automatic crow. I don't know, let's do it for layer steep. We would crow our own decision tree. And now we would see its first splits on the torque. And as well, therefore, the torque would have, in this case, the most importance, then the rotational speed, then the cycle, tool wear. And if we would now delete all of those and just do one split, we could now see as well, okay, how pure the torque, for instance, can split this. And we could check how this would look for the rotational speed, for the cycle time, for the air temperature. And we could see how good it would split. And we could as well manually create those splits or adapt those splits. So we as well fully customize that one to learn by ourselves how an information gain or like a Gini index or something like this would work. And we could as well understand with that or explain by ourselves really good how the feature selection process would work. That's a really nice way to explain in the end, and it supports you explaining the feature selection process. So much to the embedded methods. So the last thing I wanted to cover, it's not actually feature selection, but at the same time, it's quite useful. It's what you call dimensionality reduction. So if we go back, sometimes we have a lot of those features and we want to strip it down to less features. So we could use, for instance, the principal component analysis, which would help us reduce the amount of features, basically by converting our feature space into a lower feature space. What does it mean? So we're having a feature space, like for instance, like here, of 5 attributes, and the PCA will now strip this down and calculate and translate this into a lower feature space. So based on 4 principal components, we can explain the same variance, basically, or in this case, we would define here either how much we would have, like in this case 4 components, or we want to explain 95% of the variance, we could configure. We would now run this. And now we would see, okay, we would need now 4 components to explain 95% of the variance of our target. So in this case, we can get rid of one attribute. Basically, we kind of got rid of the information of one column, and because with 4 principal components, we could explain 95% of the variance. So basically what a PCA does, you can imagine it like it moves around the coordinate system and tries to find principal components which are describing the variance. And with that, you can break down your data set, basically your data frame, into a lower dimensional space. And with that, you reduce the computational power. And that's quite nicely used to reduce a feature space. And with that, you will still have 95% of the variance, which in this case would mean you still have like 95% of the information in your data. Another nice thing is with that you can directly get rid as well of outliers, because with those 95% of the variance, you will lose most likely the outliers, which are according just for small pieces of the variance, and you would get rid of those. So it's super nice at the same time to filter out outliers, while at the same time just keeping the important information of your data set. And another nice methods to use for dimensionality reduction is ISOMAP, PCA, TSNE, autoencoders. Like autoencoders basically will as well, like it's a neural net which encodes, it decodes a higher dimensional space into a lower dimensional space and then back up, and then basically checks how it differentiates between the encoding and the decoding. And basically, if there's a high error, then there's some anomaly or like there's something in the data. While if it's able to encode and decode it, then there's not an anomaly in the data. For instance, this is how an autoencoder works. And as well, this concept you can use to reduce the dimensionalities if you have a lot of features in. So basically, long story short, to work with your features and your feature weights, you could either do filtering, use univariate, like correlation, weights, so on, or you could use so you could either use like filtering, or you could use wrapper methods. You could use the model weights like tree-based, linear, logistic, SVMs, neural nets, or you could use dimensional reduction methods like TSNE, PCAs, isomaps, autoencoders. And basically with those four, I would say, streams of methods, basically you have all you need to perform feature selection. And I think now I'm already a little bit over the time I should have taken to talk about feature selection. And now if there are any questions, I will open it up for discussions.
I don't see any questions right now, but while we have the audience, let me launch our poll question so we can vote on the topic we'd like to decide and select on while folks think of their questions. So for those, if you have your screen widely open, you'll have to probably minimize it in order to select our topic for our next session. So would you like to learn more about the Python Learner, deploying processes via the AI Hub, how to handle images? And if you select the other, when we have our closing survey, when we close this out, you'll have a survey that will ask you for some feedback on what we can do for improvements, and you can submit the topic there that you'd like to cover. So looks like we are reaching our voting. So again, make sure you select one topic. And we'll count down 5, 4, 3, 2, 1. So it looks like we're at a 50-50 split here. So we'll check if it's going to be Claudio or Jeff, our speaker. We'll see which one that they'd like to cover, or maybe they might be able to cover both, but we'll take a look. We'll definitely get it updated to see which topic will be our key starter. Thank you for voting. By the way, if you look in the chat, I did post the link to our AI Studio past webinars you've been asking for. We finally have them uploaded to our how-to video. They're also within our user community site, so you can now have those to go back and play on those past sessions that we had, like working with the LLMs, Hugging Face, and et cetera that we've had previously. And again, if you don't have a topic about the featured selection, we can dive into anything else. And I don't know, Claudio, if there's any other tips you would recommend when working with featured selections. I think you showed earlier, if someone wanted to know a little bit more, it would show how to use it, I think, when you highlighted.
Yes, so basically for each operator, if you don't know how to do it, go to the help section and jump to the tutorial process. And there will be a nice example on how it will be used. Together with the help section, you actually can tackle any type of problem quite well.
Sounds great.
Otherwise, reach out to us. We're happy to support you as well on your journey.
Well, let me get my slide deck while folks still think of questions. Just had some closing slides. So let's change presenter real quick. And let me select my screen. So again, this is what I'm going to share is our PowerPoint. Again, if you didn't have a chance to download it from the handout section, you'll have the list links to those helpful websites. I'll have to add, I think I have it in here, the YouTube. Nope. I will add that to update for the next time, have that YouTube how-to channel as a resource that you can review those past sessions. And again, within the user community, you can post comments that can go to our experts and other existing fellow peers. So if you had other questions, we'd be able to address them. Documentation you can find here within the documentation section of the community. You want to fine-tune your AI Studio skill sets. We have our RapidMiner Academy. We also have some of those courses within our e-learning site. So up in the top of the community, you'll see a Learn where you can come and take those courses. Marketplace is where you'll find the latest clients when we have a new updated release. You search the Data Analytics Solution Suite and you'll see the AI Studio, or you can just even type in AI Studio and search. Next upcoming event is our Q2 sessions. The registration page will be updated hopefully by March 28th. So today's our last session for this Q1. So again, March 28th, that page will be updated where you'll be able to see the opportunity to register for our upcoming sessions, April, May, and June. So that's all I have. And let me go back to Claudio. All right. Well, everyone, thank you so much for joining us today. We'll end early, give you back 15 minutes of your time. Hopefully this was helpful. And again, we'll get this recording up to both the user community and to our YouTube how-to channel. Thank you. Have a great day, everybody. Thank you, Claudio.
Thank you.
Bye now.